Thank you, Alex. So, and thank you everyone for coming. So actually, because I was a backup speaker, I had to decide on a title for the seminar. I think I was way too ambitious when I decided the title and the abstract. I decided to basically put everything there. And so I wanted to talk. There's two topics I was interested in perhaps talking. One of them either testing dark compact objects, or whether we'll get there afterwards, or dark matter with gravitational waves. I don't think I will have the time. I have slides about this second part of dark matter. I might not get there. So if you came for this part, I'm sorry, but I hope you like the talk. But I'll focus mainly on this first part of testing dark compact objects. And the reason why this is interesting is because, well, as you know, we're sort of living what you could call a new golden age for gravitation after the so-called golden age in the 60s, 70s. But this new golden age is not theoretical in nature. I would say it's becoming experimental in the sense that we now have a bunch of data from gravitational waves in the Event Horizon Telescope that I've shown, for example, that very compact dark objects exist. They form binaries, they merge. Most likely, there are photon rings around them, and all this data is opening really new doors for potential discoveries, and in regimes that we haven't basically tested so far until basically these discoveries that happened in the last 6 years or 7 years now. But this is only really the beginning. So this right now we are really at the first steps of this new age, and especially in terms of gravitational waves in the coming decades. There will be new gravitational detectors that are planned, so Centra and so-called fourth-generation ground-based detectors like the Axions telescope or Cosmic Explorer, which are proposed future detectors here on Earth. And these detectors will be much more sensitive than LIGO. They will detect, for example, this first gravitational wave that you see here from the first event that LIGO detected. You see a lot of noise in here. With third generation detectors, the noise will be basically the noise will be the thing that we will not probably see in this plot with the same event actually. So we will be doing what we can call precision gravitational physics, and we also will likely be doing, let's say, our science might start to be driven by the data and not the opposite. Right now, it basically we have the theoretical models. We try to get gravitational waves out of the noise, but in the future, it's likely that actually the data will tell us something about fundamental physics or astrophysics, etc. So these two facts really open the door for plenty of room for unexpected discoveries, which is the topic of some of my work in the past few years, and especially in terms of trying to understand or understand what you can learn with gravitational waves in terms of fundamental physics. And there's, of course, this is not you can put many more topics in here. Just putting 3 topics on which I've been personally involved. So the typical stuff that you can do with gravitational waves, for example, will be to test GR, test general relativity, test whether gravity is well described by general relativity around these binary black holes. For example, this plot, I'm not going to explain what this is, but this plot essentially shows you that so far, the inspiral of 2 binary black holes is fully consistent in terms of fully consistent with general relativity within some error bars. Right now, we are not really in the regime where we are proving this in a very precise way. The error bars are still large, so there's still room for unexpected discoveries. But in the future, these error bars, so this probability distribution that you see here will become narrower and narrower, and that's where the discoveries might happen. Besides testing gravity, there's 2 other topics that I'm especially fond of. One of them is the possibility to search for dark matter and new fundamental fields with gravitational waves. a particular topic that I might or might not talk today will be about the possibility to detect ultralight bosons, so bosonic field, bosonic particles that have masses that go between 10 to the minus 20 volts and 10 to the minus 10 electrovolts, so really light particles. Some of them have been proposed, for example, as dark matter candidates, and there's been a lot of work in showing that you can actually use gravitational waves to detect these fields. And well, if I have time, hopefully I will tell you more about that. But in the majority of the talk, I will speak about something else, which is about testing compact objects. In particular, testing the nature of the compact objects that made up a binary system from which you detect the gravitational wave. And the reason why you want to, of course, test what are these two objects made of is because the fundamental question that you can ask first is whether these two objects are actually the black hole solutions of general relativity, the Schwarzschild metric or the Kerr solution if you're talking about a spinning black hole. So you can quantify this possibility and then ask, for example, whether you could, for example, detect other exotic species that are not, for example, black holes or not neutron stars, or the two type of compact objects that we detect so far, and I think probably made up all the type of sources that we'll detect. But perhaps there are other exotic species that we haven't thought about, or even there's plenty of proposals of new of other type of exotic objects like boson stars, or objects that will be almost as compact almost as compact as a black hole, but they are not real. They are not a black hole, and perhaps you could detect those objects. And in particular, there's been proposals of trying to find signatures of quantum gravity near at the horizon scale using gravitational waves. That will not my topic of the talk. I can tell you much more about this, but that's the type of science that you might want to do. And this nature of the objects are basically encoded in the gravitational waveform in different ways. So if you consider two objects that are very far apart, essentially these two objects are essentially behave as point particles. They have no structure. They're just two objects that are going around each other with no structure, and so the gravitational waveform that they emit essentially the same, almost the same, at least depending on their precision, but at finite precision, they are basically the same gravitational wave signal that you detect depending on the object when they are very far apart. As they come closer together, you start seeing the structure of these objects, and you start having effects, for example, tidal effects, the fact that these objects are being tidally distorted by the other one. You start seeing the multipolar structure, which will be the topic of this talk, or that I will talk about. So basically, you start seeing the structure, the fact that these bodies are not perhaps completely spherically symmetric. They might have an oblate shape or even more complicated. And as you come even closer, and you start having effects, for example, absorption effects, or what is called tyrant-emitting, related basically to absorption of the radiation, of gravitational radiation in the object surface. And that all these effects together can allow you to distinguish between, for example, black holes and other type of subjects. Then when these objects come really close together, you have a merger, you have a post-merger, and in the merger, that's where things can become very complicated. In principle, you will need, let's say, numerical activities to completely describe the process. In general, for most objects, this part is completely uncharted territory. But after in the post-merger, there's plenty of work, and you can have different effects depending on the object that you form. You can have so-called echoes. You can have the signal can decay and have a ring down that decays in a different way than the black holes in general relativity. If it's an object, let's say, that is a bit not very compact, you can have tidal disruption, etc., etc. But for the remainder of this talk, so now I want to talk about recent work where we look more in this part of the multipolar structure of the body. So this is work that was on the archive since more or less 1 month now, done in collaboration with people in Rome, so Nick Nicola Trell, Andrea Mantelli, and Paolo Pani. I should say that without Nicola Trell, this work would have never been done. He was really the big mind behind this work, I would say. But so let me give you a sort of reminder what these multiple moments and multipolar structure is. So I'm going to remind you in Newtonian gravity, or you can describe, for example, the gravitational potential of a given source with some density rho. If you write down the Poisson's equation for the gravitational potential for some source, outside the source, you can describe the gravitational potential for a generic density profile as an expansion in spherical harmonics. And basically, which is also, if you want an expansion in 1 over r. So where, for example, the L equals 0 component will be the mass, essentially gives you the mass of the object. In general, the L equal 1, the dipole is actually 0 in general because it's related to basically a choice of coordinates. So you can always put it to 0 if you choose the center of mass, the body center of mass to be the center of the origin. But then at L equal 2, you get, for example, a quadrupole, etc. Just like in electrodynamics. There's 2 different ways to describe this multipolar structure. I'm introducing the 2 because I will use both actually in the talk. So there's this spherical harmonic decomposition, and you can also do this decomposition in terms of what are called symmetric trace-free tensors. So there are tensors that are symmetric and trace-free, and this notation basically means that you're making these objects symmetric and symmetric in the indices and trace-free. That's what these brackets mean. You take a tensor and you make it symmetric and trace-free. And I'm not going to explain. If you want to more details, you can go to this classical book by Wesson and Will. It's a very nice book where all these things are introduced. These moments, this STF tensor can be described. These multiple moments in the spherical harmonic decomposition are related to these symmetric trace-free tensors through an expansion in terms of what are called symmetric trace-free harmonics, which are related to spherical harmonics. I'm not going into the detail here, but it's essentially you can relate both tensors. So, for example, and this L is basically the number of indices here. So L equal 2, for example, or if you have 2 indices, you're talking about a quadrupole. If you have 3 indices, you are talking about the octupole. If you have 1 index, about a dipole, etc. And no indices at all is basically the mass. And there's some properties that are important here. So if you have an axisymmetric body, for spherical, if the body is spherically symmetric, all multipoles except the mass, except the 0, 0 component here are basically 0. The object is fully described by the mass. If you have an axisymmetric body, basically all the moments with m equals 0, with m different than 0 vanish. And if you have a body that, for example, is besides axisymmetric being equatorially symmetric, for any L that is odd, these multiple moments also vanish, and that will become important later on. So in general relativity, there's a generalization of this multipolar structure. Things become much more complicated in GR. Was first introduced by different people that different, let's say, formulations of this multipolar structure by Yarrow and Hansen, and then by Kim Thorne. And there's proof that actually all these formulations are equivalent. But at the end, what these formulations tell you that if you have a stationary asymptotically flat spacetime, you can describe the metric asymptotically in terms of its mass multiple moments and what are called current multiple moments that have no Newtonian equivalent. So the mass multiple moments are the equivalent of the mass multiple moments that appear in Newtonian gravity, but these current multiple moments are something really related to gravity, and it's related basically to the angular momentum of the spacetime. And for example, in this Kip Thorne's formulation, you can read off these multiple moments in terms of the asymptotics of the spacetime in some given coordinates. And for example, in the GTT component of the metric, you can read off the mass multipoles. In the GT5, for example, components, you can read the current multiples. For example, the L equal 1 here. For example, well, the SL equal 1 will correspond to the spin of the spacetime, for example, and then you can have as many multiples as you want. And these quantities here are just what called axial vector harmonics. They are related to spherical harmonics, but for vector fields, is not important for the moment. And for example, for a Kerr black hole, things are become very simple. So a Kerr black hole is axisymmetric and equatorial symmetric, and so all m's vanish besides the m equals 0. And the Kerr black hole also only depends on basically its mass and its spin because of Noether theorem. And so all the multipoles can be written only in terms of the mass of the black hole and the spin of this black hole. And so basically you only need these two numbers to completely describe all the multiple moments of the Kerr metric. And so that's where gravitational waves become important, because this multipolar structure actually was shown to be imprinted in essentially the gravitational waves that are emitted by a binary system. So the multipolar structure of each body. This is work by Ryan in the 90s. And for example, if you imagine an spiral of a very small body with some mass mu orbiting an axisymmetric and equatorially symmetric spacetime, where here I'm meaning this is a v, so the orbital velocity much smaller than 1, which is this parameter. So this is a post-Newtonian expansion, if you want, some expansion in v in the orbital velocity. So this is only valid really at large distance when the orbital velocity is small, and you can expand the gravitational wave spectrum in terms of the frequency in basically this formula that was derived by Ryan. So, and what's important here is that you get terms basically that depend on different multiples in the spectrum. So, for example, you get this term, which is essentially the current dipole, so essentially the spin of the massive object, or the most massive object. And you get terms, for example, that depends on the mass quadrupole. And then if you go to higher orders in this in the orbital velocity, you start getting higher order multiples. So the gravitational wave actually basically all these multiples are imprinted in the gravitational wave. And so, for example, if you measure, because the Kerr spacetime only depends on two numbers, so mass and spin, if you measure the mass and the spin of the black hole plus, for example, you will measure its mass quadrupole, you can basically completely test the geometry of the spacetime in principle by cross-checking that the mass quadrupole is consistent with the mass and the spin that you measure. And actually, this mass quadrupole can be very well measured, or it's thought that it will be very well measured with what are called extreme mass ratio spiral, which are exactly these bodies where you have a small body orbiting a much more massive one. And so, for example, deviations from the Kerr quadrupole will be measurable with a very small 10 to the minus 4, 10 to the minus 2, depending on the system. So you'll be basically measuring the quadrupole moment of supermassive black holes very well with LISA. So now the question is, so far I was talking about basically the case where you have the Ryan's theorem of the previous slide only applies for axisymmetry and equatorial symmetry. But I mean, there's no reason why you should believe that an object has to have exactly the same symmetries as a Kerr black hole. Well, I'm giving you an example. I know Guillaume is not here, but taken from a review by him. So this is a Kerr black hole. I'm not going to explain what are the colors. The Kerr black hole, they essentially completely axisymmetric, equatorial symmetric under the equator. But you can have objects such as fuzzballs. Don't ask me what they are. They are something coming from string theory, but that can have multiple structures that are they have no symmetries at all. They are not equatorially symmetric. They are not axisymmetric. And you can think about, for example, just the Earth. The Earth is neither equatorially symmetric, neither axisymmetric. It is, to a good approximation, very well described by a spheroid, but in reality, there's mountains, then there's whatever. So there's no reason why you should believe, why you should think that all the symmetries need to be kept.
But in this case, the particles, they are stationary.
Yeah, I'm still talking about stationary objects. I'm not saying where these come from. I'm just saying, well, perhaps you can test these possibilities. There's very recent work that appeared almost at the same time as our paper where they studied non-equatorially symmetric case, but still symmetric. So in this case, you get current quadrupoles. So the S with L equal 2, which are not there if you are in exactly an equatorially symmetric case. And they show that this equatorial symmetry of the spacetime with extreme mass ratio installed can be measured at the order of 1% in their work. But still, we wanted to go even further and basically consider the case where no symmetries at all, and there's basically I have all multiples, and my spacetime is not axisymmetric, is not equatorially symmetric, etc. So for that, so what we considered was essentially at leading order, aside from mass and spin, the first term that appears in the equations is basically related to the mass quadrupole of the object. And I'm going to consider a generic mass quadrupole in the sense that, if you remember the formula, it's a mass quadrupole that has, L equal 2, but the M that appears in the expansion can be 0, 1, or 2, or -1. Or -2. So to do that, so the setup is basically I have two objects, one object with M1 and 2. They are orbiting each other. They are very far apart, so I'm still considering, the dual interval, if you want, where I can use a post-Newtonian formulation. And in the post-Newtonian formulation, the orbital dynamics can be effectively described in terms of a Lagrangian. So there's many works on these topics, on showing how you can arrive to such a Lagrangian, which is essentially a correction to the Newtonian or two-body Lagrangian, which to leading order in this mass quadrupole. So this was derived in this paper in 2000. Well, it was derived in previous papers, but they put everything together here in this paper in 2014. And so this Lagrangian will basically, there's a part which is essentially the point particle part, then there's spin contributions, and then this mass quadrupole in the Lagrangian that is part that is interesting for us. This point particle part, for example, will have a Newtonian part. So these are just, you might be familiar with this formula. So these was two-body dynamics in Newtonian gravity, the reduced mass, total mass of the system. And then you have post-Newtonian corrections, which are up to, let's say, the order at which we are interested, which ends up being the C to the -4 in an expansion, in this post-Newtonian expansion. In principle, I have to consider everything up to the two post-Newtonian order. And then you have this term, this mass quadrupole, which has this form, was derived in these papers, and enters with basically with an effective quadrupole. It's a combination of the quadrupole of body 1 and body 2. This and eta here are basically the mass ratios, and well, it's basically total mass or its mass. This notation here, this n is basically the unit radial vector of in terms of the orbital radius. And this Lagrangian has a conserved energy that is important actually when you want to compute gravitational radiation afterwards. And basically, in terms of if you only consider the Newtonian part and the quadrupole as this formula, then you can add, of course, you have to add post-Newtonian corrections, etc. So in terms of equations of motion, when you take the Lagrangian, you apply Euler's Lagrange. Well, you apply the Euler's Lagrange equations. You get the equation of motion. They are schematically basically written in this form. I wrote it in this form. This part, of course, is just the velocity, is just derivative of the coordinates. And then I wrote it in this form, which will become clear afterwards. Well, you have a Newtonian part plus perturbations, and these perturbations in general, they have higher post-Newtonian terms, they have spin, mass quadrupole, etc. So if this perturbation force is 0, you have exactly the Keplerian motion. You only have the Newtonian parts of the equations. And if you I'm gonna define what I call the bond frame. So it's a frame that it's basically a frame where, for example, if you add the spin, will be aligned with the spin of the body of the body. In the case of quadrupole, is a frame where I'll fix my quadrupole, where I define the quadrupole of the object. This frame is in fact arbitrary. You can define it in whatever way you want. But in terms of this frame that I defined here, you have 5 contingent motion in the Kepler problem. So it can be semilatus retum, the Newtonian eccentricity, the inclination of the orbit with respect to that to this frame. So essentially the inclination of the, if you want, of the orbital angular momentum with respect to the z-axis. And then you have what is called the longitude of pericenter and the longitude of the ascending node. So these 2 angles here. And these 5 quantities in Newtonian gravity, they are constants of motion. Just apart, this V here is what's called the true anomaly, which is related to the orbital phase, to these formulas. Just to be complete. But here, of course, we are not in Newtonian gravity, so these we want to solve this full problem. So that's where, for example, Nick, so the guy that the first author of this paper, were becoming important. So I took over this project. We were starting this project more or less 1.5 years ago, and I naively just wanted to solve these equations, where putting here the quadrupole term and trying to solve the equations brute force, and it was almost impossible to do it. With a generic quadrupole, it was difficult, etc. And I was completely ignorant about these, about, for example, celestial mechanics, etc. And it's a problem that is, very common in celestial mechanics, where you have a perturbing force to the Newtonian problem, and as being used, for example, in post-Newtonian theory, etc. But I didn't know about it. So Nick arrived and he saw how this problem can be solved using basically what I call this method of oscillating orbital elements, where basically you take this perturbing force, where in this case we will consider it to be the quadrupole term, because we are only interested in understanding what is the leading term in the leading correction in these post-Newtonian corrections, in these post-Newtonian expansions. So we are considering that this perturbation force is basically the quadrupole part, and we will neglect things. This for simplicity. This mostly for simplicity, this part here. But we'll consider that this perturbing force is a small force on top of the Newtonian problem. And well, this in the post-Newtonian approximation, this is always the case, right? In the early spiral, this is always the case, because the quadrupole goes as 1 over r cube. So if r is very large, it is smaller than the Newtonian part. And so the problem essentially, or the way to solve this in perturbation theory, is to consider that basically the orbits are essentially given by the Keplerian orbits, but where the orbital elements, so these mu a, which I recall are basically these 5 orbital elements, become functions of time. They slowly vary because you have this additional force in the problem. And so if you plug in this in the equations, essentially in the equation of motion, you get an expansion, because you now have this additional function of time here that basically, so you expand the derivatives and you get, so this term here basically just the velocity, and if you want this to be equal to the Keplerian, velocity, basically this term has to be 0. And if you do the same for the velocity parts, you get essentially you get this equation by basically putting this equal to this, right? And then this has to be equal to this. And so these two equations give you equations that give you the variation of the orbital elements as a function of time if you are in the presence of this perturbing force. So this is something that is used quite commonly in celestial mechanics. For example, if you have a third body in the problem, that's the way you could, for example, compute the corrections to the orbit, to the presence of third orbit, etc. How much time do I have?
You should be having about 15 more minutes.
15, okay. So these perturb force basically introduce a new time scale in the problem. In general, is longer than the orbital time scale. And this leads to a secular changes of these orbital elements. So they are constants in Newtonian problem, and then they slowly vary because of the presence of this perturbing force. And so to solve this equation, is what you can do is use so-called multi-scale analysis. So use the fact that you have two time scales. You have the orbital time scale. You have a longer time scale related to the presence of this perturbing force. So a way to get rid of the short time scale related to the orbits, basically time average everything. So you average over the orbital phase. So when you do that, so these again, this is a very common thing. You can find all the formulas in the for example, in Poisson and Wills. It's just applying basically formulas that are already known for a problem. But when you do that, basically you see that what you get is for the simulatus rate and then for the eccentricity in this particular problem when you add the quadrupole. There's no secular changes of these two quantities, but they oscillate on the orbital time scale. But because I'm time averaging these here, and these corrections disappear. The inclination angle actually has a so-called nutation. So it's called, so you have the orbit, you have the body, and this object, the plane of the orbit respect to the object starts going around because of the presence of this of the quadrupoles. And here I'm defining a bunch of new quantities which are related to the fact. Well, we are doing this expansion, just simplifies the equation through all these multiple moments, so the 2-1, the 2-2, the etc. We are expanding them in terms of a real part and imaginary part. It makes the equation much simpler to work in this doing that. And this Q0 is essentially the axisymmetric part of the multiples. So, and you see, for example, here you have no Q0, so that there's for example, when the non-axisymmetric part is exactly equal to 0, so all these numbers here are exactly equal to 0. The orbital plane basically doesn't, it doesn't go around. That only happens when you have the non-axisymmetric part. Perhaps it's easier if I show you again the picture. For example, the inclination is this angle, right? So if the angle change, basically the orbital plane with respect to the z-axis moves essentially, and that only happens if you have non-axisymmetric corrections. The other two angles essentially also depend very in a complicated way with the multiples. They depend on the axisymmetric part as well. So even when there's non-axisymmetry, even when the quadrupole is axisymmetric, meaning when Q1, Q2 is equal to 0, they are still non-zero. And this actually is related to the fact that you have the pericenter advances, just like first in post-Newtonian theory, you also have an advance of the pericenter. So it's famous general relativistic effects. So essentially, because these angles move over time, the pericenter, which here is here in this picture, moves over time because of the presence of quadrupole. And that actually happens even without the axisymmetric part. That's a generic thing that always happens.
So this notation is periodic.
This notation, yeah. So that's next slide. It's periodic, but it's periodic with a new. There's a new phase that enters in the problem, which is related basically to this quantity that appears. There's always this quantity you see here. Well, basically these numbers here. That's always the same. Right? Gives you basically if you want a new time scale.
Session and notation on the top. That's what I expect.
You have both. So yeah, actually, so these equations give you both.
Right? And then on the top you have a little wave on the top.
Exactly.
Okay.
And you see because you have these two angles advanced, so the orbit goes around, and then but also moves, right?
But this is very Newtonian. Let's say, what is the signature on?
Yeah, that will be
okay.
like, let's say the final part.
Okay, thank you.
So, but before understanding the gravitational signal, you have to understand the Newtonian problem. So we found closed form. I'm not going to show you the forms because they are in the paper. They're complicated. But we found closed form solutions for some particular case. For example, if the n equal 1 part is 0, you can find actually completely closed form solutions to the equations. To the equations in the previous slide. for generic, when you have this Q2, you have both m equal 1 and m equal 2, we solve the problem perturbatively in terms of considering that the non-axisymmetric part is smaller, is small compared to the axisymmetric part of the multiple. So we define these quantities that are in this plot, so they are essentially a ratio between non-axisymmetric part and axisymmetric parts. We define also these phases will appear later on. This is not super important, it's just to tell you, well, there's a bunch of quantities that appear in slides that might become confusing, but when you solve the equations, it becomes useful to define these quantities. For example, this epsilon 2 so appears here, and this phase. So when you solve the problem, there's always this number that appears, so this psi 2 that appears always in the equation, and we solve it. Always every solution appears as a sine and cosines, etc., of this phase psi 2 when you solve the equations. For example, and here I'm showing, for example, the inclination angle for the solution that we found as a function of psi 2. Here there's two plots, one because below is a difference between a completely numerical solution of the equations and the analytical solution that you can find in the paper. Well, and basically this just so that the analytical solution that we have actually describes quite well the problem. The important plot is this one on the top, so this is the inclination angle. These three different curves are essentially different magnitudes of the n equal 1 multiple. We fixed the n equal 2 to some number. But the important point is that you see the inclination angle oscillates with some given phase, and the phase that's basically that it's periodic essentially in this psi 2 in the psi 2 quantity that you can get by solving the equation. So essentially, this, if you want, is a new time scale in the problem related to the precession of the orbital plane that appears in the problem. I have what, 5 minutes?
When you say numerical solution to the problem,
I say solving this equation numerically.
right, but with the time averages.
Yeah.
I'll be more than 5 minutes. 7.
5 minutes. Okay.
5, 7.
Yeah. Okay. I have to speed up a bit, but I think I can.
I mean, take your time.
So just a side note, because it's part important, when you compute gravitational radiation, we actually compute only for the circular orbits, because it's simpler than considering fully eccentric orbits. And actually, this part is a part that I wasn't aware of. I learned about this. So first of all, you need to have the complete solution. Well, you might recall that the similarities and the eccentricity, they don't vary on the secular time scale, but they vary on the orbital time scale. And actually, if you want to have the full solution at the leading solution, you actually have to solve the full oscillating equation without time range for them. For those two quantities, we do that in the paper. But there's an important point when you do that, is that these P and Z are the oscillating similarities and eccentricity. They are not the real eccentricity of the problem, right? So if you want the Newtonian, for example, this eccentricity is the Newtonian eccentricity. When you add the perturbation, it's just a number, right? It doesn't mean that it's the real eccentricity of the orbit. And what this means is basically, if you take the E equals 0 in the full solution after you solve the oscillating equations, the Z going to 0, for example, doesn't necessarily mean that you're going to the circular orbits limit, because it's not the true, it stops being the true eccentricity of the problem. This is actually a problem that is known in post-Newtonian theory. For example, when you add post-Newtonian terms, you get various definition of the eccentricity. For example, there's first post-Newtonian order, for example, there's these quasi-Caperian parameterizations where you get different eccentricities in the problem. And so we had the same problem here. If you go to the literature, there's a bunch of definitions of eccentricity. We choose to basically describe the problem in terms of two new quantities, which are defined in this way. So this is the mu eccentricity and similarities rating. It's basically computed in terms of the phase of the phase at the pericenter and at the phase of the apocenter. So on both sides of the orbit. And the reason why this is useful is first because these are fully invariant quantities. These just relate to the phase. And in the circular limit, basically this goes to 0. And in Newtonian limit, this goes to basically the same numbers throughout the definition of eccentricity in Newtonian gravity. And so what we mean by taking circular orbit, basically we mean taking this quantity going to 0. So this is just a side note that when you do this oscillating approach, you have to be careful about what you mean by circular orbit. So you have to be careful that when you take the naive eccentricity to go to 0, you're actually going to the circular limit, because it doesn't always happen. So the last minutes, I want to now tell you what happens in terms of gravitational emission. So now basically we solve the conserved part, so the part where I'm neglecting gravitational radiation. And now I'm going to put gravitational emission in the problem. In gravitational emission, I add yet an additional timescale related to this radiation reaction, which is typically also, at least in the early spiral, if you go sufficiently far in the spiral, is longer than this processing timescale I was talking about that appears because of the quadrupole, and is also which in turn is longer than the orbital timescale. So a typical way to solve this problem is essentially to basically use the quadrupole formula to compute the flux in it. So you have your you have all the dynamics that you computed, and then you plug in that in the so-called quadrupole formula, for the famous quadrupole formula, that gives you the flux in gravitational waves for a given object that's following a given binary, in this case, that is following a given path. So well, these are basically the coordinates of the orbits. This is the quadrupole moment of the binary, not of the objects. And I should say that because we are considering that the quadrupole moment of the individual object is fixed, so it doesn't depend on time. There's no term here that depends on the time derivatives of the body's quadrupole, right? It only depends on the quadrupole of the whole system, of the binary system. And then you can plug in that in a so-called flux flow balance. So you say that the orbital energy decays because of having gravitational radiation that you can compute. And to close everything, you have to basically solve all these equations. So again, there's a bunch of details I'm skipping here. And you can, for example, at the end, we can compute let's say the orbital phase that appears in the gravitational waveform. Because you're considering now things that happens on the radiation reaction time scale, it's useful to also do an average over the processing phase that appears in all the equations that we solved. But you do an average over this processing time scale, and this gives you all the quantities like orbital phase or gravitational wave phase if you want, etc., etc. So this U here, this U tilde here is basically if you want the post-Newtonian parameter, so it depends on the frequency. It's basically a measure of the frequency of the orbital frequency, which is just 1 over the orbital timescale, or orbital period. Sorry. So those are the typical steps that you will take in the problem. So we did that, and then you have to go to the R power, compute the waveform. So the way to do that is again using the quadrupole approximation. So you plug in that in the metric perturbation. These are very standard calculations. And then because what you observe is useful to go to so-called TT gauge, where you have these two polarization, H plus and H cross. You project this tensor symmetric perturbation in the TT gauge. So using again standard formulas, and the H plus and H cross, you can write them in a combined way in this form, in a schematic form, where you get essentially an amplitude. So you get amplitudes that depend on this inclination angle and this omega, which was one of the other angles that appeared in the problem. And recall that these angles not depend on time, so you have an amplitude that depends on time, that is modulating due to the fact that these angles depend on time. And you have a phase that basically depends on the orbital phase. So in terms of data analysis, it's more useful to construct waveforms in the frequency domain. So to do that, normally the typical thing is to consider what is called the stationary phase approximation. This stationary phase approximation works for the case where you have non-precessing objects, orbits. In case where you have precessing orbits, and that's having precessing orbit is something that also happens if you have spins, for example, or it can happen if you have spins. So this is something that is known not to be handled and not to find approximation to frequency to Fourier transforms of these quantities. For example, you can go to this paper where they found a way to compute Fourier transforms in the case where you have precessing orbits, and using a technique that they call the shifted uniform asymptotics. Again, you can go to the paper and see the details for all these derived, but the point here is at the end you get a frequency domain, that waveform that depends on some phase and some amplitudes. So that's the part that is unique to one having quadrupoles and then having non-axisymmetric quadrupoles. So these amplitude functions that appear in the amplitudes of the waveform, they are modulated. So it is the frequency. So the different amplitudes as a function of frequency, and they are modulated due to the fact that the angular momentum, so the orbital angular momentum, is precessing over time. And there's differences between the axisymmetric and the non-axisymmetric case. So here, for example, the black lines, they correspond to the axisymmetric quadrupole, and the red and blue lines correspond to different choices of the non-axisymmetric part. So for the spheroidal case, or basically the axisymmetric case, one peculiar thing is that, for example, for a finite inclination angle, this A0. So just to recall you, this A0 is basically, it's an expansion in spin-weighted spherical harmonics. So it corresponds to the m equals 0 in this spherical harmonic decomposition. It's constant in the spheroidal case, but it oscillates for the non-axisymmetric case. And the fact that you have also modulations in the other amplitudes here, is even for the axisymmetric case, is related to the fact that we chose for this plot a non-zero inclination angle. If you go to exactly zero inclination angle, which remains a constant in the axisymmetric case, actually only the m equal 2 in the gravitational wave becomes a non-vanishing.
Is this an extreme mass ratio or equal
this
mass?
equal mass? Sorry, I forgot to say.
Equal mass.
Yeah, because here we are not doing anything. We are just showing how things look like. We haven't done in terms of we haven't done a more deeper analysis difference in terms of mass ratio. So there's this unique thing, and then the last important thing is the gravitational wave phase. So essentially in the gravitational phase, all the corrections appear at the same order. So they appear as for you that are familiar with that, they appear as a two post-Newtonian correction, but they all appear in some combination of different. So they all appear the same order, and they appear in terms of some combination of numbers. So I'll come back to these points in the last slide, but if you compute, for example, the phase difference between having a non-axisymmetric quadrupole and having an axisymmetric quadrupole, which is what is shown in this plot. So this is the total phase in the case where you have some axisymmetric non-axisymmetric correction. Sorry, so when these epsilons are different than 0, with respect to the case where you have you have a purely axisymmetric quadrupole, and this phase different oscillates. Right, it's basically related to this, again, to this precession. It can be as large as these are completely random numbers. It's unclear whether they apply to any a realistic model, for example. But in principle, for some given numbers, you can make this phase difference between these two sufficiently large. So let's say 1 radian or slightly less, that in principle you could hope to detect it. What is unclear right now, and this is the part that we haven't done, is of course there's a bunch of degeneracies. If you want to do, all these terms, they will enter at the same PN phase, the same post-Newtonian phase. So perhaps you might only be able to measure, let's say, a combination of all these numbers and not really the, not really the axisymmetric and the non-axisymmetric parts separately. Or that's unclear, and that's something that we want to test in the future. Is there's these amplitude modulations that are different whether you have axisymmetry or not. Perhaps this helps breaking this generality. So these are future directions of what we want to, for example, do Fisher matrix analysis for different systems. Again, extreme mass ratio in spirals are likely to be the best in laser, likely to be the best objects for measuring these, but the accurate modeling of extreme mass ratio in spirals actually hard. And of course, we want to include more physics, more multiples, etc. But the important point is that if you measure these for example, the fact that you have non-axisymmetric and non-equatorially symmetric objects, this will be if you measure something like that, you will immediately tell this cannot be a parabolic. So this will be really a smoothing gum and something nice to go after. Besides, testing some fundamental properties of a black hole in general and all the future.
Thank you very much. Do we have questions for Richard?
So I have two questions, Michael. So the first is, do we really want to do accurate modeling? I mean, I can complicate my system as much as I want. Nobody's going to do match filtering to search for that. I mean, you replace 3 parameters more, it's gone. You go for power, right?
Right. No, I mean in terms of of course. But I mean in terms of, for example, imagine that you want actually to test this with, that's also true even without just a quadrupole, for example. If you want to test it with memories, all the tests assume, for example, waveforms that are not useful in reality, right? And so just testing the pure fact that an object has a quadrupole, you will, as a quadrupole different than care, you will need much better models in reality than the ones that have been used so far, right? So and that's something that people have written tens of pages, a bunch of papers on the subject. But in reality, we have no waveforms to actually do that in the future, right?
Yeah. So that's my question. I mean, in terms of 20 years ahead, do you really think this is a good thing to do, or?
I think for memories, it's one of the best things you can do. Yes. I mean, just because your test is.
But we don't understand memories now with GR.
I'm not saying it's going to be done in the next 10, 20 years. I think in 100 years, perhaps we'll not be alive, might be doable, and you always have the data to look back on. So eventually it might be done.
The other question is, you're saying that the radiation reaction time scale is larger than the dissection time scale. Is this out of the equations?
Yeah, you can see it in the equation. Well, you can see it. Well, you can see it from the side. First, it appears as everything appears as a 2pn relative to pn, relative to the linear. And radiation reaction, if you consider radiation reaction force, it comes at 2.5.
So actually, I had a question.
So it works as long as you're sufficiently far apart.
But so there's something you're neglecting there. If I take a non-axisymmetric body and I make it spin around this axis, it's going to emit with this, right? This is not included.
Yeah, well, but it's not included. So there's a paper, I think Eric Poisson, because this precession, as I said, there's no notation, but there is still precession if you have a quadrupole. And Eric Poisson estimated, I don't remember the exact number, I estimate so much in which PN order this will enter. It enters a much larger PN order than.
No, we can't. I mean, come on.
I can show you the paper, but
it's the PN order is irrelevant. I don't care how far it is from the other guy. It only depends on the spin on this side.
Okay, I have to check again the paper. Yeah. Because I'm pretty sure I had exactly the same question, and I'm pretty sure I look into it, and I think it comes at higher order, but I might be wrong.
Yeah.
Very thank you for the thought. I think the risk is a little similar to what you were saying. Correct. Two parts. The first one is you are making a very high precision calculation in C to -4, very much detailed. And maybe I misunderstood. You said you are very near your axiom that is just circular. Just have one.
Yeah, in the end, yes.
But you, for this kind of precision, you expect that actually you cannot treat it as that. You should have radiation in animals. And for this kind of precision,
well, yeah.
okay,
I mean,
anyway, but you are testing your idea.
yeah, I mean, you can always make the model more and more complicated, of course.
No, it's not the point. You make a statement, say, I'm using these to use data to test my idea.
So we are not using the data.
Okay, fair enough. Okay, but you know,
But yeah,
if you can all-
yeah.
okay, fair
But no, I see. Of
enough.
course. For example, well, to give you an example, why I go so far, most of the models they use assume circular orbits.
Okay.
Well, basically all of them.
Okay.
They are starting to look into eccentricity, but that's something. I mean, just the modeling is harder, so it's just computing waveforms is harder for.
But actually, there,
So-
sorry, there we know, and that was the question I had. We know that the eccentricity goes to zero because gravitational emission does that. Do you know that it does that? This is
No, no, well, no. I don't know. I don't know the answer.
so
That's something that can be
Yeah,
in principle.
yeah, that's
Now is I can guess, but I want to tell. Because for me,
yeah,
I
right.
can always guess. I can always guess wrong. You can tell. When you make this no asymmetric, I will tend to be some kind of symmetry because the object is very, very compact. How can and you mean even if it is very small, how you motivate that from a theoretical point of view? Now you can always say like
Well,
why
first,
not to test, but
yeah. First of all, I just think. Well,
well, you talk
There-
about
there-
small or whatever.
yeah. So that's a
really
particular amount, very
difficult for a
exotic.
compact object
It's very
to have
extremely
something not
exotic.
kind of symmetry.
But I mean, I just think about the fact. If you, I mean, I'm just
You are
thinking.
testing.
I might be naive, but I'm just thinking, for example, about the Earth. I mean, there's a
No,
bunch
I
of.
agree, but still, if you go to a compact object, your mountain is very small.
Well, but a small
But you can- I
mountain.
think that will be you can exploit, you can test like this.
When you go to very compact objects, a small mountain might mean a very large.
Okay, fair.
Because it might be small in terms of, but it doesn't mean.
Yeah, but it could be any huge impact in terms of the impact on the
Right.
the signature of the sensor.
It might not be. I don't know exact numbers, but
Sure, fair enough. Okay. You can test that. You can
in
test
principle,
the
yeah.
model.
Yeah, that's something.
You can say, let's imagine that I have a certain degree of symmetry regard to the
Right.
spherical thing, and therefore sees the symmetry.
Yeah, that's something that actually we wanted. For example, we wanted to at least have some numbers in terms of
Sure.
whether you can constrain anything with your detectors using.
Have you
and
looked at
then
this kind of effect?
no,
because
but
basically
that's something that we
you can
wanted
do
to.
it.
Yeah, we wanted to do. We haven't done it yet.
Okay, thank you.
Thanks. More questions? Okay, that's no. Can you say a highlight from the dark matter bit in 1 minute? Is that enough of a challenge?
Well, I have here.
Oh, perfect, perfect.
Wow.
Well, not this long, but I mean, I'm just gonna show the slide.
Oh, we have a lot of seminars for next year.
Yeah, so essentially, well, there's a bunch of ways to, as this plot shows, as this figure shows, a bunch of ways to test dark matter with gravitational waves. It's not necessarily exhaustive, but so there's, for example, you can think about dark matter that forms exotic stars, let's say, like stellar stars, I don't know, boson stars, etc. If this boson star is made of bosons that are dark matter. The part that I was going to talk is more like
This is the talk we are talking about, right?
Yeah.
It's just because, you know,
that I put in the abstract just because
No,
I had to
fair
do
enough.
something quick and then didn't talk about. Which is essentially you can form these clouds of ultralight fields around black holes, and there's a bunch of signatures, including direct gravitational emissions from these clouds, or signatures if these clouds are if you have black holes with these clouds in binaries, for example,
okay.
you get different signatures. Well, for example, if you have a cloud around a black hole, these will, in principle, as long as they are sufficiently far away, even the, let's say, the multipolar structure that the bodies have,
Okay.
and that's good.
All right, thank you. So yeah, no more questions then. Let's thank our speaker again.
If you enjoyed the video, like and subscribe.